In this video, we're going to talk about colligative properties. And colligative properties are properties that depend on the amount of dissolved solute. So it depends on the concentration of our solution. It doesn't really depend on the identity of that solute. So whether it's sodium chloride or calcium chloride, that isn't as important as to whether it's 1 molar or 2 molar. So colligative properties, properties that depend on the amount of dissolved solute in solution. And there's 4 of them. I'm just going to list them here. Our first one is vapor pressure lowering. So a solution, and we'll assume aqueous solutions here, it doesn't have to be, but assuming an aqueous solution, if I was to compare that, right, its vapor pressure to the vapor pressure of water, so the pure solvent, the vapor pressure of the solution is going to be lower than that of the pure solvent. So a sodium chloride solution is going to have a lower vapor pressure than water. So the vapor pressure, P-vape, remember, was our abbreviation for vapor pressure. Remember, vapor pressure was the pressure felt in a gas above a liquid in a closed container, right? So if I had a beaker of just like water and I put a lid on it, some of those gas particles or some of those water particles, right, are going to escape that solution. They're going to evaporate, and I'm going to have gas build up. So the more gas particles we have building up over that liquid, the higher my pressure. Right? If we have stronger intermolecular forces, we had less vapor pressure because less liquid, right, particles are forming or going into that gas state. So the vapor pressure, P-vape, of a solution is lower than that of its pure solvent. If it wasn't an aqueous solution, let's say it was a solution dissolved in carbon tetrachloride, then we would be comparing the solution to carbon tetrachloride. So whatever the solvent is in that solution, you're comparing the solution to that solvent. And the vapor pressure of the solution is going to be lower. And then since it's a colligative property, if I have a 1 molar solution compared to a 2 molar solution, the 2 molar solution is going to even be lower yet. So the more concentrated your solution, the more pronounced this effect. We do have an equation that we can use, and that equation tells us that the vapor pressure of my solution, so I'm just going to do P for pressure, it is vapor pressure though for my solution, is going to be equal to the vapor pressure of my solvent multiplied by the mole fraction. And it is going to be the mole fraction of the solvent. We maybe put an L in here. So if we were to take the mole fraction of my solvent, which is going to be a little bit backwards, usually when we've been doing mole fractions, I do solute on top, but my component in this case is going to be solvent. So if we were to take that mole fraction, multiply it by the vapor pressure of my pure solvent, we end up with the vapor pressure of my solution. Remember, mole fractions are always a number less than 1. So if I take my solvent, right, multiply it by a fraction less than 1, I'm going to end up with a smaller number for the vapor pressure of my solution. And we can do an example after I go through our other types here. Our second one is going to be boiling point elevation. So the name kind of tells us, right, what it is. If we were to compare the boiling point of a solution to the boiling point of a pure solvent, the boiling point of that solution is going to be higher. So salt water has a higher boiling point than pure water does. So the boiling point, BP, of a solution, right, is elevated, so is higher than that of the pure solvent. and an equation for this one. And be careful on this one. What we're solving for here is my temperature change. So how much is it elevated by? This isn't the new boiling point, it's the change. So once we solve for that change, we then have to add it to the boiling point. We know to add because it's boiling point elevation, right? To calculate our new boiling point. I'm putting a B there for boiling point. We're gonna have a very similar equation for freezing points, and I'll put an F there to differentiate. Multiplied by KB, which is a constant, is equal to KB, which is a constant, multiplied by my molality. So let's actually write some of these. This is, remember, lowercase m was my molality, and then KB I said was a constant, and it's called our Molal, boiling point elevation constant, which is a mouthful. It is characteristic of the substance. So if I'm using carbon tetrachloride, it's going to be a different value than if I'm using water. That would be given as part of the problem, unless that's what we were trying to solve for. And then, as I mentioned, be careful, this is our temperature change. So our change in boiling point. And we will do an example, I promise, after we go through our other types. So number 3 is going to be very similar to boiling point, but really just the opposite. So it's going to be freezing point depression for solutions. So freezing point depression of solutions. So as it says, right, at the freezing point of our solution is going to be depressed, is going to be lower. So the freezing point of a solution is lower than that of the pure solvent. So again, if we were comparing salt water to water, salt water is going to have the lower freezing point. My equation, delta T with an F this time, is equal to Kf times M, M still being my molality. Kf is the Molal freezing point depression constant. And then this is my change in freezing point. We will do an example, but once we solve for that change, then we need to subtract it from the original freezing point. When we are solving for the change for boiling point, we need to add it, right? My boiling point is elevated, it's higher, so we add it. My freezing point is depressed, so we're going to subtract that change. Our fourth colligative property then has to do with osmotic pressure, and I'm just going to talk about this one really briefly. There's more pressure, the more concentrated the solution. But what osmosis is it's the movement of solvent. So be really careful to not get diffusion and osmosis, right, mixed together. So osmosis, we're moving the solvent. So if I have a salt water solution on one side, that's more concentrated. So let's say that this is a 1 molar solution. And then this is just a 0.5 molar solution. And then this dotted line is a semi-permeable membrane. Meaning that some things can get through and then other things can't. And if we're talking about osmosis, we're actually going to be talking about the movement of water. And the water is going to move in the direction that essentially dilutes the solution. So it's going to move from the lower concentration of sodium chloride, which is actually the higher concentration of water, right, to the opposite direction. So water is moving from the lower solute concentration to the higher solute concentration, which is, right, from the higher solvent concentration to the lower solvent concentration. So it's water, my solvent, moving across. Some sodium chloride can move too, but we're really just talking about that sodium chloride, or sorry, about that water, so the solvent moving. And then the higher the concentration, the more pressure there is. So just know that as the concentration goes up, that osmotic pressure goes up. We're not going to have an equation for this. Beyond knowing that osmotic pressure is a fourth colligative property, that's really all we need to know for that one. I'm going to go through an example. So we're going to do one with vapor pressure, and then we'll do a boiling point, freezing point one also. The vapor pressure one, I should mention this, if we go back up, this equation is assuming that the solute itself isn't volatile. By volatile, I mean, will it evaporate? So we're assuming here that it's only the solvent that's contributing to the vapor pressure. If my solute also could evaporate, which happens, if we have a liquid-liquid solution, it's possible that both the solvent and the solute could evaporate, then we would need to take that into account also. We're only going to do it for non-volatile solutes. So we're assuming that only the solvent evaporates, the solute doesn't. If both evaporated, we would actually add to this. It's equal to the vapor pressure of the solvent times the mole fraction of the solvent plus the vapor pressure of the solute times the mole fraction of the solute. So we would just add to it. We're just going to stick to non-volatile solutes, however. So back down to our example. We want to know what is the vapor pressure, and we'll calculate it in millimeters of mercury of a solution made by dissolving 18.3 grams of sodium chloride in 500.0 grams of water at 70 degrees Celsius, which is pretty dang hot. The vapor pressure of water at 70 degrees Celsius is 233.7 millimeters of mercury. We don't really need the temperature for the problem. The reason it's stated is that evaporation, right, depends on the temperature. Something's going to evaporate more at 70 degrees than it would at 20 degrees. So vapor pressure, right, the amount of gas particles above that liquid as it evaporates, is going to be dependent on the temperature. So the vapor pressure of water, if you go to look it up, you're going to get a chart giving you vapor pressures at different temperatures. So the temperature is just stated so we know what values to use. So we're going to use our equation. We're solving for the vapor pressure of my solution. That's going to be equal to the vapor pressure of my solvent, which is given to us in the problem, multiplied by the mole fraction of that solvent. So we essentially just need to calculate that mole fraction and then multiply it by the vapor pressure of my solvent. Remember, it's the mole fraction of the solvent, so what I want is moles of water, right? Water is going to be my component in this case over my total number of moles. Sorry about the resizing here. So I am going to calculate moles of sodium chloride, we're going to calculate moles of water, and then determine that mole fraction for my solvent, which is water. So I'm going to take my mass of sodium chloride, we're going to divide it by the molar mass of sodium chloride, so grabbing our periodic table, and then I'm adding 1 sodium to 1 chlorine. Hopefully you guys are playing along. And we get 58.44 grams per mole. So when I divide that into 18.3, we get 0.313 moles of sodium chloride. I have 500 grams of water, divided by its molar mass. So 2 hydrogen, 1 oxygen, so it comes out to 18.02, and then I'm dividing that out, and I get 27.7 moles of water. So before we figure out our mole fraction, we do need to note that sodium chloride in water is soluble. right? Remember, if I was to take sodium chloride, put it in water, I don't have sodium chloride, right? What I have is I have sodium ions and chloride ions. We can write that equation here, right? If I was to take NaCl, put it in water, I get Na plus Cl minus. And we do need to consider that when we're figuring out our total number of moles of solute, right? If I was to put coefficients in front of this, 1 mole of sodium chloride gives me 1 mole of sodium plus 1 mole of chlorine. If I had 10 moles of sodium chloride, I would have 10 moles of sodium and 10 moles of chloride, right? If I have 0.313 moles of sodium chloride, what I have is 0.313 moles of sodium, right? Because it's a 1-to-1 ratio, and 0.313 moles of chloride. So in solution, what I have total is 0.626 moles of ions. And then that's the number I'm going to use to add to my moles of water to figure out my total moles. So if something is soluble, we need to take that into account, right? NaCl does not exist in water. I have sodium ions and chloride ions. For every 1 sodium, I have 1 chloride. So for every 0.313 sodium, I have 0.313 chloride, giving me 0.626 moles of ions total, right? When sodium chloride separates, I get 2 things. So I need to take both of those into account. Just kind of to continue with that, if I had calcium chloride, right, that's going to separate into 1 calcium and 2 chlorides. So just keeping the numbers straightforward, if I had 0.5 moles of calcium chloride, I'd have 0.5 moles of calcium, but I'd have 1 mole of chloride, right? Because it's a 2 in front of it, right? For every 1 calcium chloride, I have 1 calcium, so my numbers are the same. But I have 2 chloride ions, so it's twice. So I have 1.5 moles of ions once that dissociates in solution. So for ionic compounds, and I'll write this down, for ionic compounds, we need to take into account the number of moles of ions, not moles of compounds, unless it's insoluble. But if it's insoluble, I'm not going to have a homogeneous mixture, so it's not going to be a solution anyway. So for solutions, let's put this in a bright color. So for ionic compounds, need to determine the number of moles of ions in solution. If it's covalent, it's not going to separate into ions, right? It's a non-electrolyte, and we don't have to worry about that. But for soluble ionic compounds in water, they're going to be completely dissociated, so we need to take that into account. So figuring out my mole fraction here, moles of water are going to go on top, 27.7 moles. And then on the bottom, my total number of moles, 27.7 moles, plus essentially 0.313 plus 0.313. I'm just going to add the 0.626 moles. So we'll divide that out. And I end up with a mole fraction of 0.978. Remember, mole fractions don't have units. Moles on top cancel with moles on the bottom. So my mole fraction of water, right, in this solution is 0.978. So to figure out my vapor pressure of my solution, we're going to take the vapor pressure of my solvent. So 233.7 millimeters of mercury. I don't have to worry about any unit conversions because this is given to me in millimeters of mercury and we're asked to solve for millimeters of mercury. I don't have to worry about it. If we were given it in atmospheres and asked to solve for millimeters of mercury, we would have to do a unit conversion. You could do it before or after. And then I'm going to multiply that by my mole fraction, 0.978. Since that doesn't have units, my answers will come out in millimeters of mercury. So grabbing my calculator again here. And I end up with 228.5 to 229 millimeters of mercury. Another example for us. So we want to know what will the freezing point, and let's do boiling point also, and boiling point of a solution that is prepared by combining 55.0 grams of glycerol, which has the chemical formula C3H5OH3, and 250.0 grams of water. It is an aqueous solution. We probably should have said that. Oh, we did. Sorry, grams of water. So my Molal boiling point elevation constant is given to us. And this is for water. Remember, we said that it does vary depending on what the substance is. And that's 0.51 degrees Celsius per molal. My freezing point, my Molal freezing point depression constant, 1.86 degrees Celsius per molal. Because it's water, we do know our initial boiling point, right? The boiling point of water in Celsius is 100 degrees, and our freezing point is 0. So once we calculate our change, we will then add or subtract from the boiling point and the freezing point to calculate the new temperatures. I do need to calculate the molality, right? If we go up and look at our equations here, we can copy them back down, right? My change is equal to that constant times the molality for both of these. So we do need to calculate our molality. So remember, molality is going to be moles of solute. So in this case, glycerol, over kilograms of solvent, in this case, water. So I do need to convert from grams to moles of glycerol. So I have 55.0 grams of C3H5OH3. We need its molar mass, so we'll calculate that real quick. So grabbing our periodic table, we do have 3 carbons. I'm going to do my hydrogens together. I have H5, so there's 5 hydrogen there, but then OH3, so an additional 3 hydrogen. So I do have 8 hydrogen total. And then I have 3 oxygen. So I get my molar mass to come out to 92.11 grams per mole. So when we divide that out, I have 0.597 moles of glycerol. I'm just going to write glycerol. That would be the C3H5OH3. Do note, this is covalent, so I don't have to worry about it, but the same thing that we did with vapor pressure, right? For ionic compounds, we need to determine the number of moles of ions in solution. So you would look to see how many ions it dissociates into, and then multiply your molality of your compound by that number. This one happens to be covalent, so I don't need to, but let's add that note so you have it in your notes. If ionic, need to determine the number of moles of ions in solution. And again, that's really important, right? In water, if it's soluble, it's going to be separated. And the reason it's so important, remember, these properties depend on the amount of dissolved solute. So if something is going to dissociate into 3 particles and it has the same concentration as something that's going to dissociate into 2 particles, the one that dissociates into 3 is going to have the more pronounced effect, right? It depends on the amount. Moles are our SI unit for amount. So we need total moles of ions if it's ionic. So do watch out for that. When we're done with this, I can kind of give us a conceptual example using the numbers that I was just talking about. But let's finish this one up first. So because this is covalently bonded, I know that, right? What we're using is it between a metal and a non-metal, or does it involve polyatomic ions, right? If it does, then ionic. If it doesn't involve polyatomic ions and it's covalently bonded, then it's going to be a non-electrolyte, right? It's not going to dissociate in water. So I have moles of glucose. I am given water in grams. I do need, to convert that to kilograms. So I'm just going to move my decimal place over 3, and I'm going to say that it's 0.2500 kilograms. So my molality, 0.597 moles divided by 0.2500 kilograms. And we'll divide that out. And I get 2.39 molar, or sorry, molal. I just did it. I told you guys to watch out for. Lowercase m is molal. So my change in temperature for when it freezes is going to be that constant. So we have to scroll back up here to get it. So 0.51. Sorry, I did freezing first because it doesn't really matter which one you did first, but I have freezing, so 1.86 degrees Celsius per molal, multiply that by 2.39 molal. So I'm typing it into my calculator, trying to. 1.86, and I get 4.45 degrees Celsius. So units, these are canceling, so I'm left with degrees Celsius. And then remember, this is my change in temperature. This is not my new temperature, right? This is only my change. So what I need to do, and we know to subtract because freezing point is depressed for solutions, is I need to take the freezing point of water, which is 0 degrees Celsius. I need to subtract that change, and I end up with a negative 4.45 degrees Celsius as my new freezing point, right? We weren't asked to calculate the change, we were actually asked to calculate that freezing point. So I do need to subtract it. Similar process with boiling point. Its constant was 0.51 degrees Celsius per molal. Multiply it by its molality. And I'm grabbing my calculator again. And I end up with 1.22 degrees Celsius. And then again, this is my change in temperature, right? We're solving for delta T, not T. So once I have that, I need to add it. And we know to add because we know that boiling points of solutions are higher, right? They're elevated. So I have 100 degrees Celsius. I'm going to add to it 1.22 degrees Celsius. And I get 101.22 degrees Celsius. I know my sig figs I'm adding, and usually we do digits after the decimal point. So since I just wrote 0 and not 0.00, it should just be 4, negative 4. And then here it would be 101. I'm just assuming that this is those are exact numbers. I'm taking them from definition. So I'm really just ignoring significant digits on the freezing point and boiling point of water. So I'm just going with the number of sig figs that I had here, or the number of digits after the decimal point. I know it's kind of weird. So again, if it was ionic, we do need to take into account the number of moles of ions in solution. We need to remember that we're solving for the change when we plug them into our formulas. So if it's for freezing point, subtract it from the freezing point of the solvent. In this case, the solvent is water. If it wasn't water, I would give you its freezing point. And then the same with the boiling point, except we're going to add it. If it wasn't water, I would give it to you. I'm assuming you know the freezing point and boiling point of water in degrees Celsius, 0 and 100. So I had said I would kind of look at this in passing. So we want to know which of the following has, let's do the highest boiling point. And we're just going to do it kind of conceptually. So A, I'm going to have a 0.5 molar sodium chloride solution. B, I'm going to have a 1.0 molar calcium chloride solution. And then C, a 1.0 molar sodium chloride solution. So we know that the more concentrated the solution, the higher the boiling point is going to be. So right away, I'm just going to rule out this one. I know that sodium chloride is going to dissolve into 2 ions, right? NaCl is going to be sodium plus chloride, so 2 ions. So I would actually take the 0.5, multiply it by 2, and that's going to give me 1 mole of ions. And I'm assuming I have 1 liter of solution. If it wasn't, we would have to adjust that. But assuming just molarity, I have, if it's 0.5 molar, I'm assuming 0.5 moles. And then with the 1 molar calcium chloride solution, right, calcium chloride is going to dissociate into 3 particles, 1 calcium and 2 chloride. So I would take the 1 and I would multiply it by 3, and I would get 3 moles of ions. Sodium chloride dissociating into 2 particles. So I'm going to multiply it by 2 moles of ions. So then these are the numbers I'm going to compare. So 1 mole, 3 moles, 2 moles. The more moles I have, the more pronounced the effect. So B is going to be my choice. Be careful. I could have done it. I'm going to change this a little bit on you. I could have done this. Oops. If I did 0.75, it's really tempting to just look at these numbers and pick C because it's the bigger one. But remember, we have to, because these are ionic and they're soluble, we have to multiply by the number of particles. So C is still 2 moles of ions, right? Because we're multiplying it by 2. 0.75 times 3, though, gives me 2.25 moles. So that's still my answer. So be careful. It's really easy on the multiple choice question to look at C and pick it because it's the biggest one, but we're forgetting that those are ions, so they do dissociate. Now, if I gave you like methanol for all of these, methanol's covalent, it does not dissociate in water. So if I had a 0.5 molar methanol solution, 0.75 molar methanol solution, and a 1 molar methanol solution, or even 3 different things that were covalent, I am going to pick C because it's not dissociating. So again, just be really careful. If it's ionic, right, we need to determine the number of ions that it's going to dissociate into.